Good morning, everyone. So let's get straight to it. Today, I'm going to be talking about the polarization performance of FARSIDE. This is a work in collaboration with Bharat, Judd, and Danny at ASU, and of course with the NEST collaboration. So first, to start off, to remind us, FARSIDE is a probe-class mission funded by NASA to place a low-frequency radio array on the far side of the moon. It stands for FARSIDE Array for Radio Science Investigations of the Dark Ages and Exoplanets. It's a wonderful collaboration between NEST, where I come into place, and most of our speakers today form that collaboration, JPL and Blue Origin. So two compelling astrophysics, two of the really interesting, unbiased view astrophysics that we can do from the moon that require low frequency observations are exoplanet studies and hydrogen cosmology of the dark ages, which Steve just wonderfully went over. So these are the two primary science cases, which is why we're going to the far side of the moon. Now, just a quick overview of what the mission concept of FARSIDE will look like. We'll have a central base lander with the base station. There'll be a high gain antenna on it for communication. The central base station will be the primary source of processing and data collection. Now, it'll have 4 solar panels from which there will be JPL axle rovers that'll get deployed. On the axle rovers will be spools of tethers, which in turn have the antennas embedded or the sensing elements embedded in them. So as these rovers get deployed, they will unroll these tethers, which have the antennas that will be sensing. Now, a little more about these individual axle rovers. They're about 2.3 meters wide or tall. And they'll have stereo cameras for navigation and booms. So the most important thing is that they'll have spools of these tethers in them. Okay, so the FARSIDE array layout, the planned nominal layout is shown on the left here. It's going to be a 4-arm spiral configuration with the central base station that we just saw. This is the top eye view. And each of the arms will be deployed by the 4 rovers. Now, as the rovers roll out, they will roll out the tethers, which have the antenna elements. What are the antenna elements? They're simple dipoles. They're going to be directly embedded in the tether. We have designed about the array will have about 128 pairs of antennas. So there'll be 2 orthogonal polarization in each of the antenna node, meaning we will have dual polarization data, which is necessary, definitely necessary for the exoplanet science case. The frequency range that we've agreed on is about 100 kilohertz to 40 megahertz based on the science cases we spoke about. And the antenna elements, the individual antenna dipoles, will be about 100 meters long. Like I said, the antenna elements will be embedded in the tether. Now, here comes the most important part of the deployment strategy, which is really advantageous and convenient, but leads into an array layout that might cause instrumental leakage, which is what I'm studying. So this little cartoon here we'll go over that in detail. So we have the tether from the previous antenna coming in. The rover will deploy the first polarization. Let's call it the X dipole. The rover will turn 90 degrees and then deploy the other dipole, the Y dipole. So now within a particular antenna, the 2 orthogonal polarizations are going to be phase offset, as shown. This is not common in radio arrays on the ground on Earth, but we are doing so with the rover so that we can take advantage of the rover deployment strategy. Now, why is this so important to look at it carefully is because, like I said, I want to study the polarization performance of FARSIDE. Why are we so keen about that? Because one of the science cases, which is the exoplanet science case, the physical mechanism behind it is the electron cyclotron maser, which produces highly circular polarized data. So we need high fidelity circular polarized data to detect these exoplanet emissions. And this offset that I'll show you a bit will cause additional polarization leakage. Note that I said additional. So any radio array will have cross polarization and polarization leakages just because of the beam and instrumental effects. This offset will add more to it. And we want to quantify that, and we want to see if we can correct that. Okay, so before we actually look at the polarization, let's look at these dipoles. What are the beam patterns of these dipoles look like? Like I said, the dipoles are embedded in the tether and they're directly on the regolith of the lunar soil. So I have simulated that case in a simulation software called FICO, used the regolith properties as such, and I'm looking at the beams on the right. So I've shown you beams for both the dipoles, the X dipole and the Y dipole, the top and bottom, and I'm showing you two cuts along the excitation axis, perpendicular to the excitation axis. As expected, they're just like flipped. So you're getting the same thing from both the dipoles, but just flipped. Now, one thing to note, the dipoles are 100 meters long, which is resonant around 1.5 megahertz. Below that frequency, it behaves like a normal dipole, albeit the gain slightly reduced. At higher frequencies, the dipole is now electrically long. We start having bifurcations in frequency. So this is something to note. And now what happens to the polarization? The way I quantified that is using molar matrices. So I plotted the 4x4 molar matrices to look at what the polarization leakages look like. Now, for the first case, I'm taking the case where the dipoles are co-located, the normal case we see on Earth too. Each of these circles are basically, the center is the zenith, the circumference is your horizon, and we're actually quantifying how much polarization we are capturing. The first column tells you what's the Stokes I polarization of the sky goes into Stokes I of the instrument Q, U, and V. Second column is the Stokes Q of the sky into the 4 components in the instrument. The third is Stokes U of the sky. The fourth is Stokes V of the sky. With this information, we know that diagonal is what we want. Ideally, the off-diagonal terms are capturing the leakages. This is the normal case without offset. Just the beam effects causes non-zero terms in the off-diagonal terms. Now, what happens if I add the offset of 50 meters between the dipoles? I'm going to go back and forth between these plots, and you can see the bottom 2 row, the leakages increase drastically. Now, what are this bottom 2 row? It's the measured Stokes U and V. Stokes V captures the circular polarization data, which I said we need high fidelity for the exoplanet science case. So this is what I wanted to say, that there is leakages because of the offset, specifically in the Stokes V polarization. This I've shown just for one frequency. What happens if I have what happens at different frequencies? Now I'm still going to show you this 4x4 plots for the different frequencies, but I'm going to average along the azimuth direction. So now again, it's the same 4x4 matrices. I just have average. So this is theta in the x-axis versus the leakage terms.
Nivedita, 1 minute warning.
Yes. And if you can see, again, it affects the last 2 rows, especially the Stokes V. You'll see that between the offset and the non-offset cases, that is the dashed line and the solid line, you'll see the differences only in the last 2 rows, which is the Stokes V. And the other thing to note, as the frequency increases, the offset leakages decrease, but they're still 2 orders of magnitude. Now, this was just the beam. The other thing that I did, just to quickly finish off, is that what if I have an image from the sky, pass it through the pipeline of FARSIDE with the beam and the offset effects? How does it affect my images? I've taken a model of the sky, which has only Stokes I, and for the non-offset case, I do get non-zero Stokes V, but it's quite low. When I add the offset, it increases by 2 to 3 orders of magnitude, but we've also formulated a correction which says that if we know the offset between the dipoles accurately, I can get back the non-offset case. So with that, I leave my discussion up. If there's time for questions, I'll take it, or I'll take it at the discussion point.
Thank you, Nivedita.